Hello, everyone. My name is Pawel Pukowski, and I would like to tell you about our work called Investigating the Impact of Hard Samples on Accuracy Reveals Inclusive Data Imbalance. Our work is motivated by a very simple question, namely, why do we notice class imbalances in balanced datasets? This is a well-known problem where if we train on a dataset that has balanced classes, we still notice that there are some classes that have better performance, better accuracy than others. And this is something that the research on classical data imbalance doesn't really answer. There is a lot of research in this area recently, and a very popular approach that we also take revolves around topological perspective, where classes are class submanifolds. Forward propagation is equivalent to disentangling those class submanifolds. Learning is equivalent to learning appropriate space transformations. And then hard samples are simply the data samples from areas that are harder to disentangle. Now, visually, let's say we have two class submanifolds which are entangled with each other. The learning process is equivalent to learning the appropriate space transformations to make them linearly separable in the final layer. Hence, there will be areas that will be harder to disentangle, and there will be areas that will be very easy to disentangle. This is something that's a very, very natural consequence of the geometrical and topological properties and relationship between class submanifolds, and it's not something that can be escaped by fixing the sampling, how it, for example, could be done in classical data imbalance. So it's a much more complicated problem. Now, the question is how to measure hardness, and there is multum of research on how to measure hardness. We only use three measures. One is model confidence from curriculum learning, another one model energy from research on out of distribution data, and the final one are strugglers, which are learning-based defined. And basically, they assume that the learning happens in two stages. The first stage is about learning easy samples, the second about learning hard samples. So in the first stage, the class submanifolds get further and further away from each other, and their radii become smaller and smaller. And in the second stage, the opposite happens. So the point, the inversion point, where this shifts, the data samples that are misclassified at this inversion point would be defined as hard samples. Now, there is a lot of research on hardness. There is a lot of research trying to answer the question we previously stated. But the thing is that as far as we know, no one has tried to formally introduce, define, or measure properties of the hardness-based within-class data imbalance, which in our opinion is the reason behind this class-level discrepancies in balanced datasets. So that's what we do. The properties of this imbalance is, first of all, that there are more easy than hard samples. On FashionNIST and CameNIST, the ratio is 1 to 6, and on MNIST, it's 1 to 13. Obviously, that would differ depending on the difficulty measure. Next, easy samples have lower sample complexity than hard samples, which means that if we want to learn easy samples, we need less of them to properly generalize onto them. And for the hard samples, the opposite is the case. We need more of hard samples to generalize onto hard samples. And final, which is the biggest difference from the classical data imbalance, easy and hard samples are mutually informative. This stems from the fact that they both are members of the same class. Hence, adding hard samples can increase performance on easy samples and vice versa. But this degree of information sharing is dataset dependent. So on FashionNIST, which is what we show here, we can see that adding easy samples does increase the performance on easy test set, but not on hard test set. Basically, the main takeaway is that we should focus on learning hard samples. We should focus on understanding hard samples, because by doing so, we can reduce the amount of compute, which is a very big issue in AutoML community, but in ML in total, and is something that is being raised within data-driven AI. Thank you very much for listening to me.